Good evening, you pre-AP, pre-Cal Bearcats. I just want to welcome you and hope that this video instruction and this flipping classroom idea will help you. Basically, we're inverting our note time with our classwork time. So in class, you'll be working on a lot of the problems that normally you might have worked on at home, and at home you'll be taking notes and getting information that will help you with the problems you work in class. A couple of reminders. Monday, be prepared to get a book, and we're going to work some problems off of the calendar in class on Monday, and you'll be using the notes that you're taking here on this video. So you can stop and pause and rewind, but I'll be looking for the notes that you took, and you'll use them to help you with the classwork. Also, just a reminder that we're taking a retest on the last test on Tuesday, and that your test corrections are due that day. You can turn them in tomorrow, but they're due on Tuesday. You will not be able to retest unless you've done all your test corrections correctly. So make sure that you've worked on those and are ready. I hope you also had a really nice homecoming weekend. All right, let's get started on rational functions. We're going to first talk in this first example just some general information about rational functions. A rational function is a polynomial, a fraction where you have a polynomial in the numerator and a polynomial in the denominator, similar to this problem that you see right here. Also, I've gone ahead and created a t-table list of x and y values over here on the left, and the graph, I've gone ahead and plotted those points. Notice something, that this last point here and the point up here at the top, those 2 points do not connect. If I started connecting the dots, they do not connect. So there's a gap in the middle. I just want you to be aware of that, and therefore the graph is not continuous. And many of our rational functions will not be continuous graphs. So I just want to bring that to your attention. Second, I want to talk to you about these branches, approach lines called asymptotes. And an asymptote is a line of a graph that gets infinitely closer at the extremes of the coordinate plane. And we're going to talk a little bit more about that. So let me go ahead and draw in our asymptotes and our graph, branches of our graph, and we'll take a look at what that looks like. So our graph will look something like this. Our branches will look something like this as I continue to draw. And on this side it will look something like this as I continue to draw. Alright, let's go ahead and fill in our asymptotes. That will also make it a little clearer about what. Alright, we have a vertical asymptote right here. This is the graph gets infinitely closer to this line, but never really touches it. And we have a horizontal asymptote right here. Again, the graph gets closer to this line, but never touches it. This is not a new concept. You did learn about this last year in Algebra 2, so hopefully it seems somewhat familiar. We're going to just add or extend that information a little bit this year. All right, so right now, our vertical asymptote, and I'm going to call it VA for vertical asymptote, is the x value, x equals 3. Notice it's where it's the 0 of the denominator. Okay, and that's kind of important. We have a horizontal asymptote, and our horizontal asymptote in this problem is at y equals 2. And we'll talk a little bit more about how to find that in just a minute. First, I want to talk a little bit about this concept of it getting closer or infinitely closer at the extremes of the coordinate plane. Extremes of the coordinate plane would mean the extreme left, the extreme right, extreme up, and extreme down. So I want to talk a little bit about that algebraically. What does that mean? So in this same example, we have y, same problem, y equals 2x over x minus 3. So let's talk first about the horizontal extremes. So let's say our graph, the x values, went extreme to the right or extreme to the left, which would be positive 1,000 or negative 1,000. It could be a million or a billion. It would go on to infinity. But let's just talk about, let's say it was 1,000. So if our x values approached, and that's what the little arrow means, positive or negative infinity. And I'm just going to say like 1,000. Okay? And it would be a lot bigger than that, but let's just use 1,000. If I plugged 1,000 back into this equation, 2 times 1,000 would be approximately 2,000. 1,000 minus 3 would be close to 1,000, so close to 1,000, but we'll just say 997. But it'd be close to 1,000, which would be approximately 2, or close to 2. It actually would be a little greater than 2, a little larger than 2. And on the negative side, it would make it a little less than. So that's when our vertical asymptote would go from negative, as we approach positive or negative infinity with our x value. So we go out here forever. I'm going to keep extending this. That graph would get closer to 2. It would be just slightly larger than 2. As the graph approached negative infinity, it would be just slightly less than 2, and so it would be out to the edge here. Okay, so one more time about our our vertical asymptote. As we our horizontal asymptote. As our x value approaches positive infinity, that goes way out here to the right or way out here to the left, as it gets larger, the x value gets infinitely larger. Then we just use 1,000 just kind of as an example. It would be approximately 2 plus a little bit, so a little greater than 2. And as we move off to negative infinity, it would be just slightly less than 2, but it would get infinitely close to that line as it moved out to its extremes. Okay, in terms of the vertical asymptote, let's look at the graph as the graph moves toward its extreme. As the graph gets closer and approaches from the right side, as you're moving from the right, so that's what we call from positive 3. As we're moving from the right, the graph is going to move toward positive infinity. And the reason is, as we move closer and closer to the right, you get closer and closer from the right, you get closer to 3. So it'd be 3 and a little bit. 3 and a little bit, or approximately 3, would give us approximately 6 at the top. And that 3 and a little bit minus 3 would be a really, really small number, but it would be a positive small number, and it would get smaller and smaller and smaller, and when you divide, you would get larger and larger and larger. So it would go off to positive infinity. As you go in from the left and you move, your x value moves toward the left, and it gets closer and closer to 3. It would be 2.999, let's say. Then when you multiply, you also get close to 6, maybe a little less than 6, but you get a little less than 3, a negative number in the bottom. So a negative tiny number in the bottom, which means it's going to go off to negative infinity. All right, that's just sort of also an overview of some basic concepts about limits that we'll learn later on in the year, but I think that's just a good heads up to where we're heading later on. All right, let's take a look now at recapping that algebraically. Okay, let's just take a look at this one more time algebraically in this same problem. So what we had, if you looked back at your graph, is that as our x values approach positive infinity, and that would be going out horizontally. So this is talking about our horizontal asymptote. As our x values approach infinity, positive and negative infinity, our graph actually approached a number, a value which was close to 2. Okay, it got closer and closer to 2. That was the asymptote. And so your horizontal asymptote was y equaled 2. And then as our x values approached 3, our graph approached positive and negative infinity. Notice as we approach infinity, the x values approach infinity, the graph approached a value, and as x approached a value, the graph approached infinity. So take a look at that. I would pause and really think on that. That's some really big concepts that's going to help you later on. And that would create a vertical asymptote at x equaled 3. All right, let's go on and take a look at a couple of other examples. All right, this is kind of the process to graphing rational functions, and let's just say, by the way, go Bearcats with great victory on last Friday night. All right, the very first thing we would do in graphing rational functions is you would try to take your example, your problem that you have, and you would want to factor everything that you could. So the first thing you want to do is factor. That's going to help us both whether we factor the numerator and the denominator. It's also going to make us aware if we can possibly simplify the function that we're given. So I'm going to go ahead and just give us a function to work with. This is f of x equals 2x squared plus 5x minus 3 and x squared minus 2x minus 8. And we're going to go ahead and factor that out. Factor the top, and we'll factor the bottom. I'm going to go over here and just remind you of the whole little slip and slide process for factoring for this one. If we slip the 2 over, you would end up with an x squared plus 5x minus 6. You would factor x and x. Multiply to negative 6, add to 5 would be a positive 6 and a negative 1. And then you would slide that 2 back into your problem underneath. And you would have x plus 3 and x minus 1/2. And remember, we then talked about changing that back to a multiplying away your fraction so that you don't have a fraction. So that would just be x plus 3, and then it would be 2x minus 1. And that would be a simple way to factor the numerator. So I'm going to go put that in over here. So we have x plus 3, and we have 2x minus 1. That's just really a review of some skills, and those skills might be on your retest that you're about to take. All right, next at the bottom, that's just a pretty simple factoring. We have an x and an x, multiply to negative 8, and of course add to negative 2. I believe that would be negative 4 and a positive 2. All right, so now we have everything factored. We have everything factored. We're going to identify your vertical asymptotes by finding the zeros of your denominator, which were your restrictions, is what we called them before. So in this case, that would be x equals 4 and x equals negative 2. And those would both be your vertical asymptotes. So in this case, you would have 2. You would have 2. And those have to do with the domain, and this has to do with your restriction. So the domain would be everything but 4 and negative 2 in this case. All right, that's our second step, is doing our vertical asymptotes. Our third step is to work on our horizontal asymptotes. And we have several rules here. We're going to compare the degree of the numerator to the denominator. All right, so we're going to compare the degree of the numerator with the denominator. I have several examples, and we're going to fall onto another page. So I want to start with this example. If I had f of x as one of my examples, and I had 3 over x plus 2, and I have g of x, which is just another example, so I'm comparing these two examples, and I have x minus 4 over x squared minus x minus 6. Okay, we're comparing the degree of the numerator with the degree of the denominator. The degree in the numerator here is a 0 degree, so we have 0 over a first degree. Over here we have a first degree over a second degree. And we're just comparing the degrees. If I look at the numerator in both of these cases is less than the denominator. The degree of the numerator is less than the denominator. If it's less on top, if the top, which is your numerator, is the top is smaller, I always say, then your horizontal asymptote will be y equals 0 every time. So if the top is smaller, your horizontal asymptote will be y equals 0. Let's move on and see what happens when the top is not the smaller degree. All right, now we're going to look at these two examples. In the first example, we have the degree of the numerator is 1, so a first degree numerator, and in the bottom a 0 degree numerator or denominator. In the second example, we have a second degree numerator and a first degree denominator. Again, we're going to compare the numerators, the top. In this case, our top is larger, so bigger top. And if the top is larger, you're going to have no horizontal asymptotes. So horizontal asymptotes is none. Often or sometimes we'll have a slant or an oblique asymptote, and I'll talk to you a little bit more about that in class tomorrow. So remind me, we will probably have that come up in an example tomorrow, and we'll take a look at that and how to find that and what to do. You're going to be using probably long division or synthetic division to find the equation of that slant or oblique asymptote. All right, our last example is we're comparing again the degrees, and in this example the degree in the numerator and the degree in the denominator are the same. So this is a second degree in the numerator and a second degree in the denominator. And on this side we have a first degree and a first degree. So again we're comparing the tops. The tops are the same. If the tops are the same, we're going to have to go to the coefficients, the leading coefficients, to determine. So we're going to use the lead coefficients to determine our horizontal asymptote. To determine, I'm abbreviating, our horizontal asymptote. All right, so in this case, this would be 2 over 1 or 2. And in this case, this would be 3 over 5 or 3/5. So our horizontal asymptote in this case would be y equals 2. And in this case, this would be y equals 3/5. All right, I'm going to go over tomorrow how we would determine if we have a slant or oblique asymptote. Also, when we do all that factoring that we did at the beginning of our problems, if we have a cancellation to simplify our rational expression, like something in the numerator will cancel with something in the denominator, we will also get something called a point of discontinuity. Last year, if you were in Algebra 2 pre-AP, we called that a hole in the graph. It is also called a removable discontinuity. So we'll talk about that tomorrow. I hope you had a really great homecoming weekend. I hope you have a great evening, and I look forward to seeing you tomorrow. Night, Bearcats.